All right, this video is meant to go over the data analysis of the momentum lab as well as momentum diagrams just very quickly here. So finish this, come down here, you got all these things to do. Probably easy way to look at it is to look at the data sheet. Okay, this is the makeup data. This makeup data was done for not the air track, so the other ones. The cars are a little bit bigger. The masses might look a little bit weird if you used the air track. And then right down here, of course, points out everything it is you need to do. We are not going to use these points of data, but this is what your data should look like, whether or not you are using your data and you finished, whether or not you're going to use mine. So for like an elastic collision, and that's what I'm going to use right here. Okay, oops, I've got it at the end of the video. We can see here that we will get, that was time 1, gathered by that guy. That was time of the second one final. And right there, your large one, is the time of the first one final. So if we switch right now to the webcam, I'll show you that this is the data that we got from that guy right there. So if you want to pause the video real quick and write that down, potentially to follow along, that's great. This number right here, which I've erased, is kind of reading. A reminder that when you use the memory function, it tells you the total of the first and second time. So this total is actually those, let's see, not that one. It would be this one over here, and this one added together. So I got this by taking the total, subtracted time 2 to get this guy right here. And then I will show that work done on the board here real quick. Okay, so of course, first thing we're going to do is we're going to find the velocities of each of them. The velocity of one initial is going to be 0.1 meters divided by 0.171 seconds. Let's go ahead and remind ourselves that the mass of one is 0.200 kilograms. Of course, those extra 2 zeros are to show that we measured it, that it is in fact that accurate. Let's see here. Time of one final is also 0.1 meters divided by the much larger time, because you saw it was going much slower in that particular case. The velocity of 2 final, initial was easy, that should be 0. Should be 0.1 meters divided by 0.186 seconds. Is that right? That's not right. No, that's right. Apologies. Okay. And the mass of number 2 was slightly less because it did not have the kind of the elastic thing. So it's 0.190 kilograms. Also pointing this out, if you're using different sized flags, be really careful right here. I'm using 2 larger flags, which is why I'm using 0.1 in both cases. Okay, so with this, you can do your calculations. Let's see, have I done that? Yeah, there we go. Okay, so this should be 0.585 meters per second. This should be very slow, 0.053 meters per second. This guy over here should be 0.538 meters per second. With all of those speeds, you should now calculate momentum. So let's go calculate momentum 1 initial, which should be 0.117 kilograms meters per second. I kind of divided this up into object 1 and object 2. I kind of wish I would have done final and initial, but that's okay. So let's just keep it going the same way. So this would be 1 final, which should be this velocity times this mass, which should get me 0.011 kilograms meters per second. And momentum of 2 final, which is this mass times this mass, should equal 0.102 kilograms meters per second. And of course, to confirm this, I should be seeing that all the initials equal to all the final. So I'm going to add both finals together. Obviously, the initial, this is just the total initial, and the total final, adding those 2 together, should be 0.113 kilograms meters per second. And looking at, we've got 0.117, 0.113. I'm off by 4 thousandths. The thousandths is not as important as the fact that that is like the 3rd decimal down. I'd say the 3rd significant figure down where it changes. And then I'm good, and now there's a change. I can say that this pretty much confirms conservation of momentum, with probably a little bit more detail in your paragraph, but I'm trying to be relatively quick with this. Now let's talk about momentum diagrams. Basically what you should show is this: hey, here's the momentum of one initial, just draw some size arrow, okay? And then I'll draw a dot for the second one to show that there is no initial. So if I add those two together, that's the total initial. That's this number, pictorially, okay? Well, how do I show that then that is equal to the final? What I can see is that this number, pretty darn close, so I'm going to say that is the momentum of 2 final. You'll notice this tiny little gap right in here. That is the momentum of 1 final. If you add 1 and you add 2 together, they should equal the total momentum of the first one. And that's a rough idea of how to do that. When you move on to other momentum diagrams, do try to make them relatively sized. So if this is the arrow that you drew for the first one, and you draw the second one, or you've done the second one and it is twice as fast or 3 times as fast, make sure you draw the arrow accordingly. Make sure you draw it to be 2 to 3 times bigger. Same thing here. You'll notice that I tried roughly to get the size of this arrow, even though I'm not being, I'm not measuring out an exact distance. I tried to get this relatively sized, like you can see here that the second momentum is pretty darn close, 0.102 to 0.117. So about, 80–90%-ish right there. So 80–90%, and then there's the leftover 1, which is why we had to capture the velocity of 1 final. And that is how to do at least the first one. If you have any more questions, just let me know.